Okay. So hopefully you have out your things. If you don't, then get them out now while I remind you what we did last time. So remember, last time I taught you, I guess Thursday, we learned the second part of the fundamental theorem, which said something similar to the first part. It said that if you take the integral of a derivative, then they kind of cancel each other out in a weird way. You just get the antiderivative at b minus the antiderivative at a. In other words, if you're trying to take the area or the integral between -2 and 3 of like any function, like in this case the constant function 6, then what you do is you take the antiderivative, as in what did I have to take the derivative of to get 6, and then plug in the top number and your bottom number and subtract the 2. So 6x was the antiderivative because when you take the derivative of it, you get 6. Okay, then you plug in 3, you plug in -2, and you subtract the 2. Same thing with cosine, antiderivative of cosine with sine, because if I take the derivative of it, I get cosine. All right, so the integral of cosine would be sine at the top number minus sine at the bottom number. Cool, okay, and then that was a big discovery that integrals and derivatives are like opposites, they're inverses of each other. They undo one another. Cool, okay. I don't know, 19 of 39.
Found it. 19 of 39?
All right, so that was the fundamental theorem that had to do with definite integrals, with numbers down here. Okay, today we're learning about this symbol, an indefinite integral, without little numbers, without bounds of integration. And all this means is take the antiderivative of this function. So let me read you what that says. Fundamental theorem of calculus gave us a method for evaluating a definite integral if we can find an antiderivative of the integrand, the guy in here. The remainder of this chapter will be dedicated to methods of finding antiderivatives, or more specifically, indefinite integrals. So again, because integrals and derivatives have this like weird connection where you like undo derivatives to take integrals, they came up with this little symbol without limits, without numbers up here, and they just said, okay, this will now mean just any antiderivative of this function. So this doesn't really mean area, this just means antiderivative until you put numbers here. Now it means area. Okay. Okay, all right. So then let's do some of these. There's not much for me to say. You'll see how this goes. Here it tells you the general rule, but I don't know. To me, this doesn't mean that much. I just always have to think about it in my brain. So watch this. If I'm trying to take the antiderivative of 2x squared plus 1, okay, you got to think in your brain, what did I have to take the derivative of to get 2x squared plus 1? So yeah, what about this? Let's just talk about the 2x squared. What did I have to take the derivative of to get 2x squared? Yeah, what the heck?
I can't remember.
Yeah, okay, so that's a good place to start. Everybody knows that the x, I mean, for sure somewhere I should have an x cubed in there, yeah?
It's just x cubed. No.
Except if I just keep it x cubed, then the derivative of x cubed would be 3x squared.
Negative x cubed?
Not negative, that would make it negative 3x squared.
Wouldn't it be over 1/2 or over 1/2?
Yeah, okay, so we don't want this 3.
Over 1/2, right?
Exactly. We don't want this 3, so we would like to cancel it somehow. So if I don't want that 3, then it should be over 3. Now if I take the derivative of this, watch what happens. I get 3x squared over 3. This piece is out. Cool. But still at 2, okay, so then I need that 2 up here.
Wow.
So then there you go. If I take the derivative of this, it's 3, cancels out the 3, and then but the 2 is still there.
That's a lot.
It is a lot to think about, but it's actually not. I'll show you. Like, here's the shortcut. In a second, I'll talk about that. All right. So there's this part done, but now the plus 1. What did I have to take the derivative of to get a plus 1? Yeah. Nice. All right, there you go. And then you might be smiling, thinking, oh, okay, I can circle this. But while this is correct, if I took the derivative of this, I would get that. But what if I took the, don't write any of this because I'm about to make a point. What if I took the derivative of this? Whoa, that also gives me that. Or what about this, 70? Whoa, or 170, or whatever. Any number out here, any constant out here would still give me the same derivative.
So do we have to put like parentheses?
And so,
How do you stop that?
that's what this guy is. This plus c right here accounts for that. So really, your answer is not just one answer, but infinitely many answers. It's this function plus some constant. Yeah. Don't forget to do it. They will check. So then there is your answer, and really what this means is now this is my family of antiderivatives of this. Cool. All right, now what I was going to say, the general case for products is, or sorry, for power like x to the n is, I mean, it says it up here. So the way I think about it is it should be one more than this and then divide by the new exponent. Just like when you were taking derivatives, if I was taking derivatives of x to the n, that would come down, so you'd be multiplying by the old guy, and then you'd subtract 1. So to undo it, you would have to, okay, so this is the derivatives. Okay, derivative of that is that. So to undo it, you would have to first bring this dude up by 1, and then divide by it. So that's why it says that. You bring it up by 1, and then divide by the new guy. Yeah. So it's one more than the current exponent, and then divide by the new guy. The only reason this is hard is because it's doing stuff backward. But if you do enough, you'll get sweet at this. All right. This was just an explanation. If you want the rule, it's up there. It's up there. Yeah, that's it. Okay. Here's another example. Evaluate that. But I mean, if I just look at that, I don't know what I have to take the derivative of to get this. This is too complicated. So sometimes it's worth simplifying the thing first and then taking the integral, or the indefinite integral. So what I mean is, let's simplify that. Watch this. If I see something plus something over something, usually you want to split that up. Okay. Hopefully that looks familiar. We've done that before. All right, then let me ask you, how would I mean, there's more that I can do to this. How would I simplify this? Oh, you're taking the antiderivative of this already? No, hang on to that. You gotta simplify it fully, and then, because it won't work the same, because of the quotient rule and all that stuff, it just won't work nicely like that. But yes, you're right. Let's make this an x to the 1/2. Let's make this an x squared. This is just me simplifying before I even do anything. All right, x to the 1/2 over x squared, I mean, they have the same base, so you can subtract those two. All right, so this could be 1 over x to the 1.5, so the 3/2, or I'm just going to write that as x to the negative 3/2. You guys see what I just did? This minus this is negative 3/2. Okay, and the same thing here. I don't want x to the second on the bottom. That to me is confusing. So let me just do it like this, so it follows the like general rule that we just saw up there. Okay, and then the general rule says, okay, now that you have x to some power, remember now what you do is okay, undoing derivatives. So you add 1 to this first, which would be what? X to the
Oh, 1.
yeah, -1/2. I agree with. That's it. -1/2, and then divide by this new exponent. So divide by -1/2. In other words, multiply by -2. Okay, and then if you're ever trying to, did I do this right? Then just take the derivative of this. If I took the derivative of this guy would come down, it would become a +1, and then this would become x to the, this minus 1 is -3/2, so we did a good job. All right, cool, and then same thing over here. So let me ask you, let's see how much you guys have picked up. What would be the antiderivative of that? Nice. -x to the -1. Yeah, and then this should be good. If I took the derivative of this, that would be plus x to the -2, which is exactly what I have. Cool, and then I'm missing one thing at the end.
C.
Nice.
Can you explain just one more time how you got from like the original to the antiderivative? Yeah.
Yeah, the whole thing.
No, just the like.
Okay, yeah. Yeah. So all I'm doing is following this rule.
That's not easy.
Which, yeah, I mean, it doesn't look easy, but it's not that bad. All you do is add 1 to this,
Okay.
and then divide by that new thing. So this plus 1 is -1/2, and then divide by -1/2, that's the same thing as multiplied by -2.
Yeah.
Okay, and same thing here, add 1 to this, it's -1, then divide by -1, that just makes it negative.
Okay.
Yeah. Yeah, like I said, it's undoing a derivative, so instead of bringing this step, like multiplying and then subtracting 1, we're doing the opposite. First adding 1, and then dividing by the exact opposite. Okay. Then here's all the other functions we know. Let's see if we can take these derivatives or these antiderivatives. Also for this one, this I think is kind of ambiguous. I read this as natural log of 2 times e to the x. So that's how I'll be doing it. That's why I always put parentheses around my stuff. That's confusing. It could be read as natural log of 2 e to the x, but then that's not as exciting because a lot of stuff could cancel. So I think this is what was meant by that problem. Now let's do it. All right. Well, I guess let's just go one by one. If I have natural log of 2 times e to the x, this one looks like it's scary. Like what the heck? Well, I don't know what I have to take the derivative of to get natural log of 2. But remember, natural log of 2 is just a constant. Yeah. So that's just out in front. So for this first guy, this would be like saying 2 times e to the x. That 2 just comes along for the right, except it's the natural log of 2. Again, that's just a constant. Right. All right, then you're thinking, okay, what did I have to take the derivative of to get e to the x? Yeah, all right, that one is not too bad. Yeah, this one, this one, just taking the derivative of it is tricky. You guys remember, not the antiderivative, but you guys remember the derivative of this? Of just 3 to the x?
No.
Yeah, most people don't. Okay, 3 to the, or anything to the x is similar to e to the x, where it kind of stays the same, but then you multiply by natural log of the base. Okay, so that's the normal derivative. Obviously here we don't have the natural log of 3, so we must have canceled that out somewhere. So to go backwards, like it says up here, to go backwards instead of multiplying by the natural log, you like divide by it. I don't know. I always just have to think about it in my head. I don't like memorize these. I always just have to undo derivatives. Okay.
Why would you just like remember that we canceled it out if you don't actually know that?
Well, because it doesn't show up. Like it's not here. You're thinking of this as a derivative. You know that normally these should have a natural log of 3 attached. I don't
That's
know.
not a derivative, is it? Or is it?
This in here you're thinking as a derivative because you're trying to undo the derivative. That's what this means, yeah. All right, anyway, okay, so this 3 to the x should be, the antiderivative of it should be 3 to the x over the natural log of 3. And then it was also over 4, and that's just a constant, so I'm going to keep that over 4 as well. So there's that part. This is like a 1/4. Like 1/4, 3 to the x. So the 1/4 stays, like, comes along for the ride. That's just a constant. That's why it's still over 4. All right, and then the one we all know that should be, that should turn into an x when I take the antiderivative of it.
Wait, sorry, so why is that ln 3, why is that?
Under. Yeah.
Maybe it's easier if let me just add the plus c, circle this. And then maybe it's easier now that we know the answer, if I were to take the derivative of this, watch this. I would get, okay, let's just do the middle part. Derivative of 3 to the x is 3 to the x times natural log of 3. This was what I just reminded you of, and then that was all over a constant, so that constant stays there. And now the natural log of 3 can piece out, and we're left with exactly that.
Yeah, but you don't have to do this.
No. Oh, I see what you're saying. No, because this is these are just a number. There's no x down here. That's not a function, so you don't have to do the quotient rule. In fact, if you wanted to do the quotient rule, I guess you could, but you'd get zeros. A lot of stuff would cancel out. All right, okay, all right. This one, you guys will be smiling. Oh, no, you won't be smiling. Never mind. This one we can't do right now, but then I asked Mr. Little, and he said he meant to flip it. So I was about to say, let's skip it, but no, let's flip it. I thought that it was, I don't know. It's only hard the first time you see it, and then you're like, you pick up on it.
Maybe not for all of us.
No, you guys will be fine with this in a
But you're a
second.
professional.
It's just hard because you're going backwards. You'll get sweet at this. Okay, yeah, this one is another fraction one. Fractions usually, like, they're too hard just to see and know that I took the derivative of some function to get this. So usually you want to simplify fractions.
So x squared over x.
That. Yeah, separate
Oh my
them.
god, and then natural log. Awesome.
All right, okay, very cool. Once you separate that, you get this, nice. X squared over x is just x plus 1 over x. Okay, this one, well, should I say this now or later?
Now.
Yeah, I guess I'll say this now. For this guy right here, the temptation is to write that as x, so x to the negative first, and then do the normal power rule. But that's not what you want to do. Yeah, because it's a natural log.
No.
There's no worries. All right, so if I wanted to get the derivative of something and get x, what was that original function? What's the antiderivative? For this part, yeah.
And get x.
Yeah, if I took the derivative of something and got x.
X squared divided by 2.
That's the thing, yeah. X squared for sure, but then if I just took the derivative of this, there'd be a 2 over here that I don't want. So let me cancel that. Okay. Or in other words, if you just want the rule, add 1 to this exponent and then divide by that new exponent. All right, cool. And then this is just a natural log of x plus natural log of x. Notice that I put an absolute value here. This is a really annoying thing that is kind of hard to explain. Yeah, you need to do it. You need to do it when you're going backwards. When you're taking the antiderivative of something, you add a little absolute value here. Because of something that I said a long time ago that nobody's going to remember, but when you take...
What did you say a long time ago?
Here it comes. All right. Okay. When you see the graph of natural log of x, notice that it's only defined to the right side of the graph, yeah? Okay. So when you take the derivative of it, let me call this f of x. F of x is equal to that, so if I take the derivative of this, then only the right side is going to be defined as well, because the original is only defined on the right side.
Why is the original not an absolute value then?
Right. Okay. So if you just have a natural log of normal x, you only get the right half. But if you do the absolute value, it does not like that. That's weird. Okay, there it is. If you do the absolute value, then you get both sides, and then notice you still get the same derivative on the left. You still get 1 over x.
How is that?
Exactly. So when you're going from the antiderivative, here this is defined on both sides. 1 over x is defined on both sides of the line. So you want the antiderivative to also be defined on both sides of the graph. So anyway, there is the thing. Let me erase that line, and then I'm missing something at the end. That should be a plus c. That's a good question. If you're on the video, the question was, is there any time where we don't need the absolute value? Short answer is no. It's always good to do it when you're taking antiderivatives. Long answer is, let's say you're wanting to take the integral from like 3 to 4 of 1 over x. Then if you don't add the absolute value, then it doesn't matter because both of these are positive anyway. So yeah, it wouldn't matter. Okay, and then are we almost done? Yeah, 2 left, and actually this I'm going to save for when we learn something else. 1 left.
And then we're done.
Right. All right, yeah, this one. Okay, let me think. What is the antiderivative of 2 cosine? Okay, 2 sine. Good job. Somebody said negative. Okay, I always have to think about these, but no. It should be positive. Because if you're going backwards, the derivative of sine is positive. Okay, so that's what I want. So this would be 2 sine of theta. And then what about negative 3 sine?
I was just looking at the sine and cosine things like reverse of taking the derivative.
Yeah.
Where sine is positive.
I know, yeah, it's always so, yeah, that always messes me up.
3 over 2. No, wait, derivative of cosine.
Wait, why? No, why? That's too hard.
It's negative 3 cosine, right?
No, not negative 3 cosine. Yeah, plus 3 cosine. Wait, what the heck? This says minus. Yes, but remember the derivative of the cos are negative. So the derivative of this would get me this negative. And then plus C, don't forget it.
Do you not need the,
Beta, oh.
Correct. D theta doesn't mean anything.
Oh, wait, yeah, my bad, sorry.
For right now, it doesn't mean anything to us. It just tells you what the variable is. Okay, then this right here, we could do using these little rules, but I don't want, like, I want you to see where these rules come from. So we're gonna learn this next. So skip. Okay, so that's what I have for you. Here comes also your homework for this week, if you're interested in practicing. Okay, and then I was just checking that your homework doesn't require any of this, and it doesn't. Why are we skipping this? Because this this kind of requires something called U substitution, which is undoing the chain rule, which is something we're not getting into till next time I teach you. Okay, and then like I just said, I was checking that your homework doesn't require this, and it doesn't. So here comes your homework for the week. It's short, like me. Oh yeah.